Cloud, start share. Okay. Go away. Okay, so the first thing I was thinking of for this was something called Coulomb's law, as well as like, so I guess Coulomb's law is kind of this one right here. It's like the force equation that when you have a charge here and a charge here, you can determine the force on one of them based on the other one based on a multitude of factors. There's this kind of constant here, which if you look at the problem, we're actually using these other units. So instead of k, Coulomb's constant, we'll use 1 over 4 pi. And this is called, I think it's called the permeativity. I always get it confused with the permeability. I think this one is magnetic fields. Yes, this is magnetic fields. So this is a mu symbol like that, and then the permeativity of free space is this little epsilon thing. So whenever you see that, it's like something you can find the value of on Wikipedia. And later on, if you saw right here, it's actually related to the speed of light, how quickly light travels through things, and that was kind of the revolution of Einstein, that like that light and relativity and all that stuff. But that's later on in the semester. But anyway, so that's what these constants. You can either use that constant where it takes into account. It's just a different unit system. It takes into account this 4 pi thingy. But we'll keep it in this one. Anyway, so it has that little proportionality constant. It tells you how strong, that basically tells you how strong the electromagnetic force is. It's a different constant for gravity, and a different constant for like the nuclear forces. And then it is proportional to the charge of one of them, the charge of the other one, and the distance between the two of them. Now here, I'm actually using absolute value signs. So this is the easier equation to remember, where here, this is pretty helpful for like, lab or tests or anything like that, because it tells you in which direction it's going. Of course, you could also just remember that, right? If this is negative and this is positive, they attract. If it's positive and positive, they repel. But a more formal way to think about it is to draw a vector r1, 2, and that's a vector that points from 2 to 1. And then it depends on the charge of the particular particles. So for instance, if one of them is positive and one of them is negative, now your F is a negative because this is negative and that's positive. And so your force vector would point in this direction, which is opposite of this kind of R1, 2 vector. But it's kind of pedantic for our purposes. We really only, we can just use this and then think, oh, okay, it's like charges repel and opposite charges attract. But, so just one more thing, that the force is also proportional to the electric field. The force, where the force takes into account both of the charges. So this would be the force felt by particle 1, so that's why I have this little 1 here, due to particle 2. So this is, we're only looking at, if you notice the forces, their vectors are with regards to what happens to particle 1. We can also do something else. We can say, what is the force on 1 due to the electric field created by this charge 2? So another way to write this force up here, instead of taking into account both of the charges, is to say that charge, this second one, creates an electric field, and then this one feels the electric field, and then the force is a result of that. So simplifying this into the electric field is more or less just taking away one of the charges. So for instance, the electric field created by charge 2 is charge 2. I'm replacing this k with this thing right here, and then 1 over r squared. However, so this was the original way I was going to try to solve this problem, but because of the particular geometry, it's actually very hard. If I were to, pick up a spot right here and try to figure out what the electric field is, I would need to do a bunch of integration and U subs and stuff like that, and it's really tedious and it's not recommended. So we're going to use something called Gauss's law, which whenever you see anything that's a circle, a sphere, a cylinder like this, always use Gauss law, because you'll see in a second once I explain what it is. It's very conducive to solving problems when there's symmetry around. So the first thing I want to introduce is this concept called flux. It is in a hand wavy kind of way, like not on the next page, I'll get to what it means explicitly, but it's kind of like how many lines. So if this was your charge 2 over here and it was positive, your electric field would be pointing away. So the way you determine that is if you were to just drop like another positive charge into this thing, if I drop the positive charge right there, where would it go? And because this is a positive charge, my electric field would go, or the other charge would go away. So you call that little extra positive charge that you dropped into the problem, you call that like a test charge, and you determine the direction of that based on the other charges in the system, and wherever that positive charge, your test charge goes, that's where your electric field vector points. So that's why these point away from a positive charge and these point towards a negative charge. So I drew these kind of out of proportion, but you could just imagine that this negative charge is smaller. So that's why I'm drawing a different amount of field lines just to get the point across with this number of field lines. So if I were to draw something like for instance, if I were to encircle this charge right here with like a dashed line or a circle, and I were to count how many lines were going through it, it would be like how much electric field is escaping through, like if I enclose it in a circle, how much electric field lines point through the outside. So for instance, if I had this positive charge with, let's just say it's a smaller charge, it only has X amount of electric field going through it. So I just drew four lines. And so I have a bigger charge with, let's say 8 lines. Because there's more electric field going through this same surface, this little dashed line I drew, this charge is bigger than this charge. And so Gauss's law can be read as the net flux, and this flux is kind of, you can envision it as like how many electric field lines are moving out of this space that you made. So this little dashed line is called a Gaussian surface based on Gauss's law. And it's equal to, and this triple equal sign, that means like that's what Gauss's law is. It's telling you that there is this correspondence, because that's not like net flux is not defined as this. I'll get down here how net flux is defined, but this triple equals is like this is what Gauss's law says, and it says that it's equal to the charge that's inside this Gaussian surface times some proportionality. This is that same permeativity of free space from before. So if we were to actually write it out in math, a symbol for the flux is like this, I think it's a capital phi. I think that's what that Greek letter is. But the net flux through a particular Gaussian surface is equal to the charge enclosed over the permeativity. But anyway, so these lines, it was just, I felt like that was, for me, that was what helped me most when I was learning what Gauss's law was. But there's actually a real definition of what the flux is. And it is the integral over the surface area. So you integrate over a surface. This is kind of like, so in maybe, I guess, Calc 2, you do, if it's the same as how I took Calc 2, Calc 2 is like lines, like you integrate, a function, because a function is just like, in one dimension or 2 dimensions. But when you talk about surfaces, you can talk about 3 dimensions. So this, well, I guess because it's a circle, it's actually just 2 dimensions. But when you integrate over a surface area and you include the electric field, so what you're doing here, this is just a mathematical way to say you're counting how many electric field lines. You're counting how much electric field pushes through that surface area. So this little dA, that's what's called a surface area element. So it's like just a chunk of the surface area. And then this thing is a surface area integral. A particularly special part in many problems, and for instance, the easiest example I can give is actually our problem, where it says that there is a uniform charge throughout, which is extremely helpful for Gauss's law. Because instead of doing actually, even though this is written, it looks a little bit daunting to do a surface integral, you rarely have to do it with Gauss's law because of how symmetric things are. So what I'm going to do is I'm going to draw our rod. This is our rod from our problem. And then I'm going to enclose it with a Gaussian surface. Let's just say that my Gaussian surface has a radius of r and a length of L. And you'll notice that the reason I chose it to be kind of this shape is based on the symmetry of the problem. Because I know that my rod is either positive or negatively charged. It doesn't, either the arrows would be pointing out or they would be pointing in towards it if it were negatively charged. And so I'm going to do that because on each side, so here and here, I would have the exact equal number of electric field lines. So that's what I mean by mimicking the symmetry. Now, because the charge was uniform, I can actually pull this E outside of the integral because it's constant over this entire thing. So it's equal up here, it's equal down here, and I don't really need to worry about it. So I'm pulling it outside of the integral. And then this is a surface area element, and this is integrating. So if you integrate over an element, you get the entire thing itself. So you actually don't need to do any integration when you see this kind of surface area integral. Rarely you do, but especially when you're first encountering Gauss's law, you rarely ever actually need to integrate anything. So Gauss's law usually ends up being, or at least the flux part of it. The flux is equal to the electric field times the surface area of the cylinder. Remember this Gaussian cylinder I made. A radius r and a length L. And the formula for the surface area of a cylinder is, it's pretty much just a circle, and then you multiply it by, I guess, L number of circles. It's like circle, 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 circle. So the area formula for a cylinder is that. And now, once I get back to my Gauss's law, remember that's flux equals Q enclosed over epsilon. I can figure out what Q enclosed is based on this, hint right here, that it's uniformly charged. So that means this guy is helpful because this is like, actually, I think I wrote it later on. Where is it? Right here? No. Yes. So a linear charge density is this thing. So this lambda here is the total amount of charge in your rod or whatever you're using divided by how long the rod is. So it's, usually you're given something and you know how much charge is in it, and then you can know how much length is in it, and it uniformly distributed means it's distributed all over the whole thing. So you can just divide the total charge by the length. Let's see. Okay, so if this is Q, right, so if this lambda is Q over L, I can rearrange it for Q and say that Q is lambda times L. And now I have that the flux is equal to this thing, and I have that the flux is equal to this thing. So now I start rearranging and canceling things. I have from my integration, but not really integrating anything, I have that one, the electric field, and then the area. And then I have Gauss's law over here telling me that it's equal to the charge density times L. And then I divide it by that little constant thingy. And notice that I have an L on both sides. So that cancels out. It doesn't actually matter how long my Gaussian surface is. And then I rearrange. I bring this thing down in the denominator. And I have this formula for outside the cylinder. Because remember, my Gaussian surface, where is it, was outside the cylinder. And so that was what the confusing part was. As soon as I started using Gauss's law, I was like, wait, isn't that just the answer for up here? But it's not. It's not quite, because it says inside the rod. So inside the rod, I need to take into account that the charge is uniformly distributed, but my Gaussian surface won't enclose all of the charge. Because if it's smaller, so imagine this is my Gaussian surface in here, like a dashed line inside the rod. There's all this charge outside my Gaussian surface that I don't get. So when I'm doing this charge enclosed, it's everything that's inside my little chunk. And because it's a chunk, it's as opposed to lines going through my thing, it's now charge, and charge occupies like 3D. It's a rod, not like a I don't know. It's not a hollow cylinder. It's a cylinder, like a volume. So that's why if I want to find how much charge is in here and it's uniformly distributed, what I'm going to do to find out how much charge is in that is I'm going to take how much volume that each of those charges can inhabit. Like if it's this big, then my charges can float around this way, 3D, or if it's this big, they can float around this way. So in order to get, and because it's uniform, that's why I'm able to make this argument that the volume ratio is the same as the charge ratio. What I'm going to do to find out what that charge is I'm going to take the ratio. I'm going to take the volume that this cylinder occupies, and the volume is, what is that? That's the surface area of a circle? Yeah, so the area of a circle and then the length. Yeah, so before we were doing surface area, so that was the circumference times L. Now we're doing the volume, so it's area times L. So that's why that formula works. And so I have that as the ratio of the volumes for the prime, my Gaussian surface, and the regular one. And then I'm going to equate that, because of the uniform condition, to the ratio of the charge enclosed and the charge enclosed. So my little Gaussian surface has a ratio, little r, so this is the ratio of my Gaussian surface. This is the whole cylinder. So it's the radius of the whole thing, charge multiplied by the charge of the whole thing. Where is it? It's not there. Not whatever. It'll drop out anyway. So let's see here. Okay, so now I have this thing. So the flux is identical because, right, the electric field is the same amount of arrows are pointing through each of these. So I have my flux from the integration from before, but now I have a different Q enclosed. Now I have little r squared, big R squared, and Q. And Q, I actually know what that is based on my linear charge density. So Q is the linear charge density over times L. So I plug that in, and I have R squared lambda L, big R squared epsilon naught. And then I divide by this thing again, and I end up with canceling some of these R's. So you see there's an R here and an R here, so I only have one in the top. And again, the L's cancel. So now I'm left with this, which I believe should be the answer to this one. And you'll notice I guess the next part in the question is just to show you that both of those things equal each other. So this expression and that expression actually do equal each other when you plug in R equals R. So I'm not exactly sure what they want you to do. I think, check your solution. I mean, I guess you can just write R there, but then it just cancels. So I think the only thing you have to do for the second one is just to replace the little r in here with a big R. I don't understand, because that's what they both equal. That's the idea, because if you plug in big R for that small r right there, one of them cancels and you just end up with that without the R there, and that's identical to this thing. So I think that's how it wants you to do that. Just either, plug in a big R there. But yeah, for this one, this is inside the surface, and so that's why you have a ratio here.
Yeah, it worked. It was the last step was pretty simple, but the derivation was so long and confusing. But now I understand it.
Yeah. So if I were to just Google, what do I Google? Coulomb's law, field of line charge. It is not easy. There's a lot of geometry or not, like trig. It's not easy. And yeah, you actually have to integrate stuff, so it looks like that. Yeah, not fun. But you know, at the end of the day, you actually end up with the same thing that you got from Gauss's law. So there's no point to do that unless your professor requires you to. Let's see. Okay, yeah. So I think either the only other option I think for the second part was just like maybe don't cancel the R's, like maybe just write a big R here, and then I don't know. But I think just plugging in big R.
I canceled it, and it was the same formula basically. Just the small r was changed into big R, and it was correct.
Okay, cool. Okay, so for the second one, I haven't finished it, but I know how to do it, and I think it's just more Gauss's law because of the symmetry of a sphere. So spheres, circles, cylinders, always, Gauss's law. And again, we see that there is a uniform charge. So first, we see that we are asked about point B. So if we take this one into consideration, so this is, it's pretty much just a giant charge because it's uniformly distributed. So instead of like a point charge Q, you can just think of it as a sphere Q. And they each have the same charge. I'll enter this into Excel as soon as we get, because I just figured out the formulas. So we have a uniform charge, and we're asked about this one. So this one is outside. So in this case, it's pretty easy. That'll be our, like we did in the first one where we did outside. So for outside, we have the same formula. The flux is equal to the surface area integral of the electric field and the area element. It's uniform, so I'm going to do the exact same thing as before. And I'm going to integrate over the dA, so it just becomes A. And then I have the surface area of a sphere, which is 4 pi r squared. So outside, now I have this thing by Gauss's law is equal to the charge enclosed over epsilon naught. I just bring the 4 pi r squared to the bottom. So this is outside. So this is what we're going to use when we determine the electric field at B due to this sphere. But if we look at this one, that B is inside the sphere. So now we have to do the same thing we did again with like the ratio, but it's a sphere inside of a sphere. So now it's pretty much just a different formula for volume. We have the volume of our tiny sphere, our tiny Gaussian surface, and the volume of the big, the actual sphere in the problem. And then we cancel some things. The 4/3 cancels for each of them. The pi cancels for each of them. And then because it's uniformly distributed charge, I'm going to replace this volume with Q prime over Q, bring the Q to this side, and then I have this. Then, just like in the last problem, The flux doesn't change. It's still the same like kind of amount of field lines penetrating our sphere. And so I equate this to Q prime enclosed over epsilon naught. And I replace it with this thing, plugging that in here. And then I bring this underneath the denominator, and I cancel out some r's because I have an r to the third up here and an r squared here. So I end up with just a regular r, and the big R stays cubed. So this is inside. So now that so this is, this was pretty much problem one, but for another circumstance. Now I have to start typing it into Excel because we actually have numbers and stuff like that. Okay, let's see. Let's increase this thingy. We'll do outside, inside.
Isn't the final Q supposed to be Q prime?
Let's see. No, because I replaced it with what it, because I don't know what Q prime is. Q prime is like an imaginary construct. It's like how much charge is in this imaginary kind of pillbox or Gaussian surface. And when I did this thing, the reason I did this was because I know what Q is. I don't know what Q prime is because Q is given to me right here. And so what I'm doing in essence is I'm figuring out what's in Q prime by the ratio of how much this sphere versus this sphere. And so that's what that argument was. It was kind of like the equating the volume that the charge can go through with how much charge is there. So that's why we keep the big Q or the regular Q, because that's what we know.
Gotcha.
Okay, so let's see. Let me just take Q here. Epsilon. Get that from Google in a second. R squared R. Let's do R out. Because that will be, I think that's given to us. Yes, it's, what is it? 30. Yeah, 30 centimeters. 3 meters. R in will be 7.5 centimeters. Yeah. 0.075. Q is, what is micro? Is that -6?
It's 10 raised to the power -3. It's milli.
No, is it milli or micro?
Micro is like mu.
Oh, you're right, of course. Milli. Okay. So 40.8 E negative. And then big R for the radius is 15.2. Okay, and then epsilon.
8.85 into 10 raised to the power -12.
8.854. Let's just do 2. E. Okay, so outside is, there we go. Here. Equals, let me do parenthesis, big Q divided by 4 times, I need to do pi again, I think it's pi, right, times epsilon times This is outside, so I'm going to do that one. Okay, I think that's right. Okay, let's try inside. That would be, what is the units of electric field? Coulombs? Probably don't even need to. Yeah, nanos per coulomb. Find the magnitude of the electric field. Newtons per coulomb? What? Okay. I just want to make sure I'm getting the units right because it says newtons per coulomb, which that's fine because it's force over charge, but it's a volt. Oh, okay, never mind. Okay. I forgot that a volt wasn't a standard unit. Okay, inside. Here, that is, well, actually, let's make sure we know the magnitude of the first one. It is a positive charge, so this will want to go in that direction. So let's just call the right positive. So this guy is positive. Oops. Okay, inside. This one is so annoying. Big Q times R inside, and then 4 pi times epsilon times big R to the third. Not right. Okay, what did I do? Okay. Oh, this thing. What is that? That was for the big Q, which is in the top. A4 should be B4. There we go. Okay, and now this one is, if this is positive, and that we're talking about it from the origin of that sphere, it should be to the left, I think. So it should be that much to the left. Yes, so the total should be the sum of those two things, with that being negative. Is that right?
And before we move on, how do you know which charge is positive and which is negative? How do you figure that?
I'm thinking both of them are positive. I'm just
Yeah.
trying to figure. Oh wait, it's the electric field. Oh, I'm sorry. It's we're talking about electric field, not force, so it doesn't matter. It doesn't matter what does it. Yeah, I think so. I was, for some reason, I thought we were like asking about force, but a property of the electric field is that it is called, what is the word for it? Superposition. It's so if you have the electric field of one charge and two charges, and all you do is add them together. So there's no minus and positive. That was my bad. I thought we were looking at forces. And the total is just the sum of those two. So I have equals sum. This guy. And this guy. Okay. And then nanos per Coulomb. I think that should be right.
Okay, so your answer was 11911, right? Into, yeah. I got the same answer, but it's not taking this. Yeah, it's not working out. Maybe we have to subtract the charge of the second one from first one, the electric field of the second charge from the electric field of first charge.
The reason I didn't think so was because they both have the same charge.
Yeah, but like maybe it's because B is in that second charge. It's located inside.
Mm-hmm.
Yeah, when I subtracted like E2, E1 from E2, it worked.
So you did this one minus this one?
Yes.
Really? Huh, okay. So inside is stronger than outside. Huh, okay. Let's see.
But I don't know like how to explain why I did that.
Let's see here. Let me go back and read the problem. I think actually I was on the right track with drawing things. Let me see. Can I draw an arrow? Arrow. Okay, so black, not what I wanted. Black, yes. If I draw an electric field away from all of these, because the sphere is positive, all the electric fields look like this.
Yeah.
And in particular, in this direction, it looks like this. However, if I draw the electric field from the other sphere, it also looks like that. And those two arrows are in opposite directions of each other. So they need to, I don't know why, like I don't understand what the, for instance, why do you do this one minus this one instead of this one minus this one? That doesn't make sense to me, but maybe it's just because of the magnitude.
Yeah, probably because even if I do the other way around, I just have to take the absolute value, I guess.
Yeah. Yeah, so I guess because it says magnitude, you're just they're asking about like that.
Yeah.
Yeah. Okay, I guess that makes sense.
Okay, that's so. Thank you so much.
Yeah, absolutely.
I was wondering if you would have any like 1 hour available tomorrow, because there is one question I wanted to do with you, but like I know you have to go somewhere, so it will be all right if we can schedule a meeting tomorrow.
Yeah, totally. I think let's see, what am I doing tomorrow? Probably three would probably be fine as well for tomorrow.
Okay, perfect. So I will email the question to you.
Cool.
All right, thank you so much.
Yeah, absolutely.
All right, I hope you enjoy your lunch.
See ya.
Bye.